So today in this video, what I really wanted to discuss was electricity. And personally, I found it quite a difficult topic in physics. And it's not so much the formulas, it's more about the concepts and how to apply these and stuff like circuits especially. So I thought today what we do is today we'll do like the part one, which in a sense will be like the theory behind all this stuff. And then we're going to see in the next video how we can apply this to stuff like circuits, potentiometers, and electronics, and how we actually use that, because that often is what I see in people tend to see the more difficult part. But first of all, let's actually think, what is electricity? And we see it in like our lights and our lamps all around us, but what actually is flowing through them? So I have my little bulb here. Excuse my. Do you know what? This is a bulb. So let's say I have my bulb here. My bulb is glowing. But what is making this glow? Well, we know that it is electrical energy being converted into light energy. We know that from primary school. Not primary school, but you're right. Now, the thing we've got to ask ourselves is, where does this electrical energy come from? You may say a battery, you may say, a power supply. And that's true. And so basically what electricity is it's really a whole bunch of these tiny little charge carrying particles called electrons. And these electrons, they carry a charge called a Q. And basically what charges is charges measured in something called coulombs. And basically, and the thing is, electrons actually travel quite, contrary to popular opinion, electrons travel really slowly in a wire. You can imagine actually, if I had a wire here, actually, let me redraw this wire. Actually, we use brown for copper. You can imagine actually the wire is like all the electrons already full in there. There's crammed of electrons already. And in fact, a common misconception that when you turn on the lights and you see an electron, go straight away from zoom into the bulb, that's not true actually. The electron kind of just goes in here, doesn't move far, and this other electrons at the end come out into the bulb. So this is a myth I wanted to just get out of the way. But the fundamental idea here to grasp was that electrons are these little tiny particles carrying charge called Coulomb. And basically, you may have heard this term current. And let's say I chuck in a few terms here. So let's say I say, oh, and I buy a bulb from the Mitre 10 Mega. I buy a bulb from the hardware shop, and it's like the bulb is 10 volts, can carry a current of 5 amps, and it has a power of 200 watts. And today we're going to use this knowledge of charge and these electrons to help break down what each of these terms mean. What is a volt? And what is an amp? And what is a watt? So let's start off first actually by looking at charge and current. Now basically what current is current, actually I'll use the proper letter. Current is equal to the amount of charge per unit time. And when you think about it, current is essentially, when you look at this definition, current is the number of electrons. Since the number of electrons is proportional to the unit charge. Because we know we have a charge constant. Now, the charge on an electron is 1.6 times 10 to the minus 19 electron volts. But basically, though, the principle behind current is current is like kind of a measure of the rate of flow of electrons per second. The more current we have in a wire, the more electrons are flowing past that point per second, because the charge will be greater. And actually, I should add to this diagram up here, we also have maybe something like 50 ohms. So that's what current is in a sense. Current is really a rate, the measure of how many electrons are going past a given point per second, because it's a measure of the rate of charge per unit time. And we know that electrons are charge-carrying molecules. Not molecules, charge-carrying particles, sorry. Now let's look at the volt. In fact, the volt is really a measure of the work done per unit charge. We'll say E over Q. And actually, and its unit is joule per coulomb. In fact, current, sorry, is coulomb per second. Well, volt is a joule per coulomb. How much energy per coulomb of charge do we need? Now, for these modern devices, let's say I had 10 volts. That means 10 joules. For every coulomb of energy, 10 joules is required to transfer that across. And how that works is, let's say I have these two. Let's say resistors. Let's say I have two resistors in the circuit. Okay. These could be anything. These could be light bulbs. These could be, TVs, whatever. And let's say this is drawing 200 volts, and this is drawing 50 volts. What does that mean? Well, what it means is that there's 200 joules of energy per coulomb of charge needed to get charge across this component. And here it's 50. So in general, devices that require more power, and devices that are bigger and need more energy, will generally have a bigger voltage. That's why, the little voltage on one of your kids' toys is a lot smaller than the voltage on like a computer or a generator. So that's what voltage is. Voltage is essentially, or a volt, is a measure of the work done or the energy needed to transfer a coulomb of charge. Now let's look at power. Sorry, we won't look at power. We'll look at ohms. Now combining these two, resistance, or an ohm, is actually the amount of volts per current. It's V over I. And what this is telling us is the resistance is the ratio of voltage across a component to the current. And that tells us the resistance, because if we think about it, if we have a very large, let's say we have a voltage of 20, there's a 20, the voltage of a device is 20, and there's a current flowing through it of only 5 amps. Our resistance would be 4. But let's say I had that same device, 20 volts, my voltmeter reading, and the current was only 2. My resistance is 10 ohms. And that makes sense, because if the current is slower, if there's less current, it means there are less electrons flowing past that point per second, because there's less charge. And because there's less electrons, it means the resistance or the material must be denser, must be impeding the path of the electrons more than another material. So that's the takeaway from this formula, that resistance measured in ohms, is equal to the voltage across a component over the current running through it. And finally, I want to discuss power. 200 watts. And power equals energy over time. Power is actually the amount of energy used per second, right? But using these other definitions here, right, since we know that energy will be the voltage times the current times the time, power can also equal actually VI. But let's not worry about that now. Let's just worry about what this base definition of power is. Now power, right, is measured in something called watts. And its base unit is joules per second. It's the amount of energy used per second time across a component. Right? If a device is more efficient, it'll have a higher power rating. Right? If a device uses 20 joules of energy in 10 seconds, the power is only 2 watts. But if a device uses 20 joules in 2 seconds, 10 watts. And this is kind of the idea of voltage as well, because really, voltage is directly proportional to power, and the higher the voltage, the higher the power of a device. And this makes sense, because if your device needs a greater current or needs more energy, it will have a greater power rating. Now, one thing to know is you will see alternate forms of these formulas. You may see power is going to equal to like I squared over R or something. Or you may see that energy equals voltage times current times time, which is another key formula. But these are all just basically all derived from these basic components of electricity: a volt, the ampere, the watt, and the ohm. And each of these measures specific quality. The volt measures voltage, the ampere measures current, the watt measures power, and the ohm measures resistance. So I hope with this we've been able to cover just real basics and the theory behind some key electricity terms. And then in the next video, what we're going to do is we're going to look at how to apply these equations to circuit diagrams and look at a bit more theory. Cool. Thanks for watching.